everyone. I'm Xin Huang. I'm going to present the paper, A Reduction from Chores Allocation to Job Scheduling. This is a joint work with Erel Segal-Halevi. Our model is the standard fair distribution model. We have a bunch of indivisible chores. Each chore can be allocated to at most one agent. And each agent has an additive valuation over the chores. And here we use positive valuations. That means when you have a larger valuation, that means you dislike the chores more. The goal is to find a fair allocation among all agents. So here the fair notions we use is maximum share. Maximum share can be considered as an extension of a cut and choose protocol. So suppose an agent is a cutter. He tries to allocate all chores in the most even way. Then the worst bundle would be the maximum share of that agent. So here is an example. Suppose that we have an agent who has the valuation like this. Then the most even way to allocate these chores is like this, because we have three agents. Suppose we have three agents. Then the worst bundle has a cost 35, so the maximum share for this agent is 35. So in general, maximum share allocation may not exist. So the interesting question is that what is the best approximation we can get? So now the largest gap is constructed by Segal, Sapir, and Tauber. So it's 44 over 43, and the best known approximation result is 11 or 9. This is work by me and Lu Pingyan. So in this work, we try to we improve the approximation result to prove that there always exist 13 or 11 approximation or maximum share allocation for the chores. So in the rest of talk, we will focus on a special instance. It's called identical ordinary instance. This is that every agent share the same ranking, but they can have different valuations. Someone could have valuations like this, another one could have valuation like this, but they all agree on the rankings. Like the cleaning would be the most difficult one, the washing the clothes could be the most easier one. And by a classic result, the ideal instance is actually the hardest instance for the maximum share allocation. That means like if you can get an approximation algorithm for the ideal instance, then you have the same approximation ratio for any instance, and the transformation is by an efficient polynomial algorithm. Also, the algorithm studied in this paper is called the HFD algorithm. This extension of phosphate decreasing algorithm for the bin packing to the chores allocation. So it runs in this way, like so because we have this ideal instance, so we first sort chores from the heaviest to the lightest. And each agent would have a threshold. You can think maybe this like a constant times maximum share. Then we start from the heaviest chores, like to ask, okay, so is there anybody can accept this chore to the bundle? If someone can accept, then we add this chore into the bundle. And we go to the next chore. If no agent can accept the chore, that means that at this chore we will exceed the threshold of every agent. Then we skip this chore and we go to the next chore, and we ask the same question. And after one round, taking the question to all the chores, then we get a bundle. Then we give the bundle to anyone who can accept this bundle. And after allocate one bundle, we will repeat this process to generate another bundle. So how this could be related to the job scheduling? The job scheduling can be considered as a special case of chores allocation. That means like the cost function is kind of are the same for each agent. And then if you consider the parallel machine, then actually the minimum span is equivalent to the maximum share, and actually, if we restrict HFFD algorithm to the job scheduling, the algorithm is actually already studied before, and here is the list of the result. So for general, the algorithm has the approximation 13 over 11 for any number of agents, and for small agents it could have a better approximation. So now let us give a bird view of our reduction. So the idea of the paper is try to reduce the chores allocation to the job scheduling. Here is when we have a bad instance for the chores allocation, then we try to construct another bad instance for the job scheduling. So what mean it's a bad instance? It's kind of from the HFD to the FFD. And for each agent I, we have the threshold alpha times the maximum share, and after running the algorithm, we assume that there are some chores unallocated. And given such kind of instance, we try to construct another instance for the FFD, which is for the job scheduling. The threshold will be some beta, it could be equal to the alpha or maybe larger, and or still some chores are unallocated. So to do this, we have in general we have two steps. So one is that we need to deal with that multi-valuation into single valuation, as that chores allocation different agents can have different valuations, but for the job scheduling, that's kind of single valuations for all the chores. And then we will, after we get a unified valuation, then we will try to trim the invalid instance to a valid instance for the job scheduling. Okay, let's look how we do the multi-valuation to a single valuation. This step is kind of easy. We just choose the agent who gets the last bundle in the HFD algorithm, and then the valuation of that agent will be the valuation which for single valuation. So here is an example. Suppose that this is the output of HFFD algorithm. Each bundle is allocated to different agents, and the blue bundle is the last bundle, and the agent omega gets that bundle. Then we choose the omega's valuation as the single valuation. Okay, after we choose this valuation, then obviously there may be some if we look at in the angle of job scheduling, there may be some invalid part. That means it will exceed the threshold. But it's not kind of an arbitrary one. For this agent omega, we can like have a useful property called first fit valid. Okay, what is this first fit valid? Like compare maybe like suppose we have like a fixed set of remaining chores, then we like just generate one bundle. One is like by the HFD and one is by the FFD. We can see the difference is that the first chore, like they're different. That chore must be like in HFD is larger than the FFD. So in another word, that each bundle is output by HFD is lexicographical larger than the output of FFD. This is the first fit valid. Okay, then our problem now reduced to like from the bad first fit valid instance to a bad instance for the FFD algorithm. Now we will deal with the invalid part. For from the invalid instance to valid instance, the idea is like try to erase those invalid chore one by one. Okay, here is kind of an example. So like the bundle in the middle is kind of invalid for the job scheduling. So what we do, like they are kind of first, like we can look at the orange one. Like orange one is like after the bundle exceed the threshold, we still like allocate some chores. For those kind of chores, we can just erase this chore. This will still like the unallocated chore is still unallocated, and we didn't we still have some invalid parts there. And for the red one, the idea is we try to trim it, okay, to trim it after below the threshold. But here we will have the problem. So if we like erase one chore, like that chore, like in the position of the previous orange one, it will not influence any of other chores. But if we like trim one chore, then we could have some butterfly effect like this. So the red one could be like if we run the FFD for the job scheduling, it will maybe allocate before and kick out some other chores, and the other chores could kick out other chores. Then we have some butterfly effect, and we will like don't know how to do that. So the idea is like try to bound this butterfly effect. So first thing we do is like we will run a tidy up procedure. The tidy up procedure is try to shrink the instance to the minimum. So we will have more structure of the instance. And after that, then we get some like then we try to do some like trim. To when we do the trim, like we try to spot the suitable reduced chore. What is a suitable reduced chore? Like it's kind we are not just trimming it. Okay, it's below the bar, then that's fine. We need like this chore satisfy like two properties. One is that the butterfly effect is bounded, so we can get an easy analysis how the process will go. And another property is that the number when we like replace the chore, the invalid chore to the suitable reduced chore. And then we run the FFD until this moment. We want to that the number of invalid chore is decreasing, so then we can use induction to prove the correctness of our algorithm. Okay, so then by this idea, we can prove actually when the threshold is greater than the 8 over 7. Oh, okay, here it should be like times maximum share, 8 over 7 of maximum share. Then we can always construct a better instance of job scheduling from Chores allocation. That means like first we have everyone have the 8 over 7 of maximum share. Then we run the HFD, some chores are unallocated. Then we finally get an instance, maybe maybe smaller number of agents, but the threshold is at least alpha, and we run the FFD algorithm, then it's still like cannot allocate all the chores. Okay, so combine this with the known result for the job scheduling, then we get actually FFD algorithm for the chores allocation has the same approximation ratio as the FFD algorithm for the job scheduling. So in general, it's like 13 or 11, and here, because all the approximation ratio is like above 8 or 7, then we get the tight ratio even for smaller numbers like 2, 3, and 4 to 7. And we also have the design an efficiency algorithm for the 1 plus epsilon approximation to the and also times 13 or 11. So here is the idea is we try to use binary search to find the threshold, because the maximum share is kind of NP hard to compute. Here, after we binary search the threshold, then we like plugging into the HFD algorithm, then we get an approximation allocation. Okay, so here we gave some open problems. So first thing is that when we design the approximation algorithm, so we have still small gap to the 13 or 11, is because like some weird behavior of HFD algorithm is kind of called non-monotonicity. That means like when you can allocate all the chores with threshold alpha, you increase the threshold, it may not allocate all the chores again. Because this weird behavior, we cannot get an efficiency algorithm exactly for the 13 or 11. And this this work shows there's a tie between the job scheduling and chores allocation. As job scheduling is kind of well-studied problem, there are many algorithms studied for job scheduling and many results for that. So it's kind of can we explore more like connection between these two areas? Okay, this my talk. Thanks for the watching.